Alrighty, students, welcome on into week 11. So week 11, meaning we only have, essentially 4 classes remaining after this one. We end on the 29th. I believe it's the 29th. Let me double check. I got my calendar right here. Yep, April 29th is our last class. So we're coming up on the end, so be sure you are keeping up on discussion boards and keeping up on the CK12 work. So I can see from over here that a lot of you were very busy over spring break. I really, really appreciate that. And I will get to grading these, I promise. And then I will also be able to show you as we have our class tonight how you can check your grade for the CK12 work. So let's hop into this week. So pretty much all the same stuff we've seen before. And now we have week 11 module, which is our plate tectonics module. And so with this one, it's sort of a springboard for the next few lectures. We're going to springboard into earthquakes. We're going to springboard into volcanoes. And we can't do that without talking about plate tectonics. So as always, the first step is going to be the discussion boards. And so you have 4 questions here and a very short video. It's about 2 minutes or less. I try to keep it very short. But this goes over the baby that would become the plate tectonics theory. And so it started off as something called continental drift and the idea of the continents drifting. And so as you watch this video, you're going to answer these questions. It's going to be a great primer for you to sort of see where this theory came from, the evidence that they use to sort of support it. And as science and technology has advanced, we've been able to confirm these ideas and hypothesize a little bit more about what might be going on within the Earth. I'll give you one of the answers right now. Number 4, why the colleagues weren't impressed. You're going to see in here the idea of continental drift was a nice one and an enticing one that they wanted to believe. But the problem was that Wegener could not provide what's called a mechanism. So if the continents were moving, why were they moving? How were they moving? Like, what was driving it? And so this is a great setup for that. So you know the discussion board flow now. So just make sure you get on there. That would be the first thing I would do. Great primer, requires no background knowledge, but gives you a little bit more to go. As we look at our CK12 work, you're going to find this will be a relatively short unit, which is nice, but we will be using, like I said, using it to springboard off into a lot of other things. A lot of people have been catching up on CK12, which I love, I appreciate. I cannot thank you enough for that. And so we see right here in April, plate tectonics introduction. And so we have a due date on this of the 15th of this month. So keep that in mind because we are drawn to an end. 2 weeks after the 15th, our class is donezo. So just 3 little sections here. Just why do that to me? Oops. So just Earth's tectonic plates, tectonic plate motions, and the theory of plate tectonics. We pretty much know the flow of this as well, but I'm going to go over it really quick. These sections give you a lot of supplemental material, be it articles, videos, study aids, little games you could play. But the main thing here is you want to use these things to supplement your knowledge from the discussion board and the lecture to answer the adaptive practices. The adaptive practice is a required portion of the unit. And so when I click on that, all it requires you to do is just get 10 questions right. And so you can have multiple tabs open to help you, maneuver through the questions so you can reference back to it. You can have, the PowerPoint we're about to go over. But that's what you'll want to use for this. Once you've wrapped all of those up, the adaptive practices for each section, you'll just have the plate tectonics quiz, and then this week will be wrapped up. So let me hop on back and we'll get right down to business here. Here we go. So here is the PowerPoint. Now with this PowerPoint, I used to group plate tectonics and the layers of the Earth together. So there's not actually a full slide here. So actually, just to say that I shouldn't say full slide. I'm not going to go over the full presentation because some of the stuff we've already seen. There are a couple cool videos to start out with. This shows how the continents has moved from 250 or 240 years, 240 million years in the past into 250 million years in the future. So it's really cool to see, based off of plate motion, what our planet will look like, millions of years down the line. And so I'm going to skip through a lot of these slides because let me hop back there. The earthquakes ones, I'm going to play it in the browser just because it's really cool. This kind of shows you, so it's global earthquake animation. So the little firing off that you're going to see is where earthquakes occur. And this was another piece of evidence that they used to establish the plate tectonic theory, because as more of these earthquakes occur, you're going to sort of realize that they create a pattern. They create these geometric shapes, almost outlining them. And this is one of the things that helped them develop the theory of plate tectonics, seeing that all these earthquakes were occurring in very similar spots, and like I said, outlining certain sections or plates, if you will. So I suggest watching it because it's really cool. And so that led them to discover the Earth's major tectonic plates. And so we see them all here. We don't need to sort of memorize them or get them right. You're always going to have this there with you. I don't quiz you on the names of the plates, but it's just nice to know. So we have some that range in size. The North American plate is huge. The Eurasian and African plate are gigantic. But then we have smaller ones like the Juan de Fuca up here off the west coast of North America. And we have like the Cocos and the Nazca plate. But they're always in constant motion. And so that leads to one of the first things we want to talk about. And so we talked about the layers of the Earth. And so now we can really hop into features of plate tectonics and the plate tectonic interactions. So all of those plates that you saw back on the slide there, they are constantly in motion. And when plates are in motion, earthquakes are going to occur. So we have a maxim that we can sort of establish saying that not all earthquakes will occur at plate boundaries. Some can occur, other places as well, where there's structural differences between rocks, but all plate boundaries will experience earthquakes. So it's kind of neat to know. And this picture on the right here, this is the Carrizo Plain, just out in still in Southern California. And if you just drive a little bit, you can walk alongside it. And essentially, what you'd be doing is you'd be walking from one lithospheric plate to the other. You'd be walking from the Pacific plate over to the North American. Our little sliver of California, and you can kind of see it down in here, but our little sliver of California is on the Pacific plate, while the rest of the country is on the North American plate. So technically, Los Angeles is slowly sliding up towards San Francisco. In about 30 million years, they should be almost neighbors. It's pretty wild. Okay. So a couple classic features of plate tectonic boundaries. We said there was earthquakes, but there's also volcanism and mountain building. So the volcanism comes from when you have these plates moving around and some like diving deep into the earth. There you have like partial melting where the magma can rise to the surface and create volcanoes. And with mountain buildings, so this picture on the right here, this is just a picture of the San Gabriel Mountains, the ones that we have up here like Mount Baldy and such. And those are being created by the interaction that we were just talking about between the Pacific plate and the North American. So they're kind of going up against each other and they get locked in this area. And when they get locked, they're still pressing. And the only thing that they can do is go up and mountain build. And so that's another feature is mountain building, or what's called orogeny. And then another feature is the stretching and thinning of the crust, because we have a motion in plate tectonics that's called divergence, which means they go away from one another. And as they move away from one another, the crust sort of thins and sort of dips. And so you get these what are called basin and ranges. The ranges are the mountains and the basins are right in between. So it's kind of cool. And these are our types of plate interactions and our types of plate boundaries. They come in three sort of different styles. So they can separate, which means that they move away from each other, which we call divergence. They can collide and come together in what we call convergence, or they could slide past each other with little to no vertical motion. And so we would call that strike slip. We'll get into names for it. It's also called transform boundaries, but it's just another type of interaction. So these interactive boundaries create their own distinct features, like the separation is what creates the thinning of the crust and the basin and range. And we'll also see that leads to seafloor spreading. The collision creates, mountain building, earthquakes, and then the sliding past one another. The features there, it could be another stretching and thinning, or you can have just, what are called like sag ponds, or like if you go out to Lake Elsinore is the result of two plates sliding away from each other and creating almost like this chasm in between where the water has filled and created Lake Elsinore. So these separating plates, when the plates move in opposite directions, we call this divergent boundaries. So to diverge means to separate from one another. So these plates are separating, they're going away from one another. And so during this process, that crust is stretched and thinned and becomes very, very fractured. So you see a lot of faulting, a lot of mountain ranges and then like basins. But this is the result of that being pulled apart. So think about just pulling apart like putty, and it would like sort of sag in the middle. Essentially the same thing that's happening here. And in those divergent boundaries, when you stretch the crust and you thin it, well, since there's not much pressure under on top, you can have magma that rises up and takes the place of that weakened crust. And so molten magma can rise and roll erupt to form new oceanic crust. And we see this down in Baja. And so the Gulf of California down here, we have the San Andreas Fault that runs, kind of cuts through California and goes under the Salton Sea and kind of comes under the Gulf of California. And so this is slowly separating little by little each year, and it will create, this new sort of open ocean basin, much more than just the Gulf. And so this is also known as seafloor spreading. So as the mantle material is brought to the surface, so you have this material that's sort of being driven up, and then as the plates thin and there's less pressure, it can go even further and further up until it pushes those plates apart. We have magma that rises up and moves the plates away, and we create new ocean floor. And so this is also called the mid-ocean ridge, because there's like a seam around the entire planet, which they talk about in CK12, that is these seafloor spreading sites. So this is how ocean basins are created, and it's a distinct feature of divergent plate boundaries. It's just one of those telltale signs, like a signature of a divergent plate boundary, is when you have seafloor spreading and magma coming up and creating new material. Now with colliding plates, so convergent boundaries, they come together. So the crust is either going to be piled up into mountain ranges by buckling, faulting, and folding, and there's great pictures of that. Or the crust can, so say if they meet, they can go up, or if they meet, the old cold slab of Earth can dive down into the planet, and then it'll start to recycle the material, and it'll like partially melt and rise up again. And that's called subduction, and it's a pretty big part of plate tectonics. And so another term for this is convergence. So when we call these convergent plate boundaries, they can kind of occur in three different styles. So you can have oceanic crust and oceanic crust coming together, in which case the old cold slab would slide down into the Earth. You can have what's called oceanic continental. So that means continental crust is colliding with oceanic crust. And oceanic crust is much more dense than continental. We've talked about that before. And so the oceanic crust would slide beneath the continent, where it would partially melt and then come up as volcanoes. Also, we could have a continental and continental interaction, where it's two continental crusts coming together, and then that just creates mountain building. So here's what we see in oceanic convergence. Two oceanic plates are colliding, and then the older, colder slab, because it's more dense, will subduct beneath the lighter and younger slab. And so we can see as the crust is being driven down in here, it gets to a point where it heats up and it melts, and it starts to rise because of density differences through the crust to create volcanoes. When we look at oceanic and continental convergence, so now we have that oceanic crust colliding with continental. Continental crust being super buoyant or less dense than oceanic crust, it won't subduct. And so the oceanic crust subducts underneath it, like we see here, once again, partially melts, rises through density differences to create volcanoes. And so this one, we'd call it like a continental volcanic arc. And so this is one of the ways like the Sierra Nevadas were made, the Andes Mountains were made, the Cascade Ranges were made. So this is the process that occurs in that type of mountain building via volcanoes. And once again, this will have a subduction zone just like the oceanic convergence. And so you also have continental convergence, which is when two continental plates come together. This is how the Himalayas were made. So continental crust is very light and buoyant, so there's not going to be a subduction zone. There's not going to be one slab going underneath the other. They're both going to stay where they are. And so this should show us a nice little, so this is India colliding with Asia, and what would create the Himalayan mountains, of which Mount Everest is a part of. So we saw at first it was that subduction zone, but then when the two continental crusts come together, they all they can do is go up because they can't sink below one another. So these are just a couple of different types of subduction zone features. You don't really get a quiz on these very much, so I'm just going to go through them really quick. So subduction zones are found when you have oceanic or oceanic continental convergence, just because you have to have that old cold slab to sink down below the lighter, younger one. And so where these plates come together, you usually get like a deep trench. So you have like the Marianas Trench, which is 7 miles deep, which means you could put Mount Everest into that trench and you would still have 2 miles of ocean above you. So those are some of the features we would see there. Other features of subduction zones, they generate frequent earthquakes, like quite a bit, and these tend to be very, very large earthquakes. But usually they're so deep that they don't cause much damage on the surface. That's not always the case, but for most of them they are. All right, well, we need to talk about this. We're going to get into volcanoes later on, so we're just going to hop through those. We're not going to worry about the subduction zones. These aren't things you're quizzed on. These are things I would usually just spend some time with in the classroom, but I want to keep this at a manageable length. And so some of the surface expressions of the subduction zones obviously are volcanoes. So you have Mount Shasta on the right, and then the mountain on the left, I believe, is Mount Rainier. And so those are both surface expressions of the subduction zone and the subsequent volcanism. So we're not going to worry about accreted terrains. That's if we had more time, we'd go into the California geologic provinces, but we really don't have that time. So now with transform boundaries, our last one, this is a type of faulting where they sort of slip and slide past one another. So it can be called many names. It could be transverse, strike slip, or lateral and oblique. And they are called conservative plate boundaries because when we had a oceanic coming together, one of those plates was sort of destroyed as it went back into the earth and rose up. Same with the continental oceanic. It was, the old cold slab was going down into the earth and being destroyed to create, the volcanic arc, which would be a continental volcanic arc. And then with divergent plate boundaries, the new material is coming up. So in those ones, either material is being created or brought up, or it's being destroyed. But with transform boundaries, since all they do is slide past one another, they're called conservative boundaries because all the landmass is conserved. Nothing's destroyed, nothing's created. And common features with these can be found at transform boundaries. You're going to have your earthquakes, and the good thing is they can record the motion of seismic events and also the amount of slip that occurs, the amount of movement that occurs. So they are absent of volcanism, and they're generally more of a network of faults rather than just one continuous line. It's like a bunch of faults rather than just one single break. These are also associated very much with divergent boundaries in the seafloor spreading centers. It's just a matter of the plate motion as things move out. They also kind of move transformly or transversely to be associated with these transform boundaries. So the Pacific and the North American plate are separated by a transform boundary. So we have the San Andreas Fault Zone, and so we are moving northwest relative to the North American plate. And so the San Andreas Fault System is just like a series of faults, but we just sort of lump it in as like one. We say the San Andreas Fault, but technically it's a system of faults. But if you just drove from Ontario up to Hesperia, you have crossed over the San Andreas Fault, and you are therefore on the North American plate as opposed to the Pacific plate. And so it's cool that we live so close to a plate boundary that we can sort of study like that. But of course, there are earthquakes associated and many, many dangers. I don't need to bore about that. So this is we want to know the mechanism. That was a big thing with Wegener, was he couldn't provide a mechanism of how this was happening. And so one of the ways that we can do that, we can sort of begin to visualize it, is through convection cycles. And we've talked about this before about hot, less dense material rising up, cooling, and then falling down. And as new material gets heated up, it rises and it creates these sort of motions. And so I'm going to skip ahead a little bit in here to where we can see more of the motion. What we can see is as it gets heated up, come on, show some good action there. As it heats up, it will rise and spread out. So this is kind of like our seafloor spreading centers, and it'll create sort of these convection cycles. So let me hop a little bit forward, and you can kind of see that this material along the sides is starting to dip back down. It will heat back up, and it'll move up, and you'll get that cycle over and over and over again. So that is the main cause of plate motion. So as we went over the layers of the Earth, we talked about the asthenosphere, and we said it was this thin little putty layer that the plate sort of rode on. And so it's not like quite melted, but it's not quite solid, and it's very, very putty-like. And it's about 100 to 200 kilometers below the surface, but it's very important because that's what the plates ride across. and that's how they're able to move. Thank you. So here's what we really are thinking about when we're talking about convection cycles. So convection cycles are, so here's the heat source of the Earth, here's the core, here's the outer core, it's very hot. It will heat up the overlying material, which will then rise to the surface and either come out through, the ocean ridge, but if there isn't one there, it just starts to move like we saw in that video, and then it'll get cold, it'll get dense, and it'll sink back into the Earth. And that's what will pull the cold slab down and create the ocean trench, as well as subduction. But this just keeps going in various convection cycles, and it keeps the plate or the tectonic plates in motion. So we're not going to worry about recent ideas because these are more just conceptual. You're not really quizzed on them, but they're just different ideas of how this convection cycle occurs and how it sort of brings material back down into the Earth and then rises it back up. But one thing to note on here is that these processes can take 60 to 70 million years. So it's not like there's these really quick cycles going on. It's this dense material that's just moving about. So there are hot spots in plate motion. We're not going to talk too much about hot spots right now. We're going to talk about them when we get into volcanoes. So I'm going to skip through this in the interest of time. But hot spots do give us an idea of plate motion, which we'll talk about with volcanoes. But so that's it. That's our lecture. I tried to keep it short and sweet. I look forward to seeing you this evening, and I hope you have a wonderful day and stay safe out there.